then I am teaching here. Okay. So that's more or less about the introduction. What I want you to do right now is you have to identify one departmental representative. I don't know who that might be. Do you have any idea?
Sir, so we have elections in a few days. So until
Okay.
then, I will be the temporary representative since I was the
Okay.
representative last year.
All right. Can you just send me an email so that I have your email ID and I don't forget. Okay.
Okay,
So
sure.
you can be my primary contact, and then you can, if there is an information that needs to be circulated, you can do that to your classmates too.
Yes,
Okay.
sir.
And the other thing, Shreya, then you have to do is to create a WhatsApp group between all the students and me. Okay. For during this class period, because if I need to, if there are any last minute changes in the class timings or any other announcement that I have to do, writing emails sometimes can be a little bit tedious from home or this environment. So if you can please make a WhatsApp group between us, and then I can make an announcement there very quickly. Okay.
Sure, sir.
All right. Fantastic. Then
Yes.
let's go back to my whiteboard again. So do you have any questions so far, guys? All right. So, so what are we expecting to study in this particular class? Okay, let me just give you a background. So the name suggests solid Earth geophysics. Okay. Now, if we think about the Earth, it has many components, of course. So we generally term them as spheres, like we have hydrosphere. I'm sure you have read about them. Lithosphere, atmosphere, and cryosphere. Okay, broadly. So what is hydrosphere? It's about the water bodies. Okay, all the water that we have around us. Okay, lithosphere is actually the solid Earth. But solid Earth doesn't only include lithosphere. We will soon see, while we talk about the internal structure of the Earth, we will see that solid Earth also includes, mantle, and then, of course, the core. But our work, I mean, our course is going to be mostly around lithosphere, okay, which is like the no from the surface to around, say, around 15 to 20 kilometers below the ground. Okay, 15 to 20 kilometers below the ground. That is what we generally call lithosphere, and that is where our most of our work, our studies will be around. Okay. Now, of course, lithosphere, this is a interactive system. I mean, it interacts with the atmosphere. It interacts with the mantle and the core, which is sitting here. Okay. So, of course, there will be references to its interaction, but then we will mostly concentrate on the lithosphere. Okay. And there is, of course, atmosphere. I don't need to say what atmosphere is. And cryosphere is generally the ice bodies that we have around. Okay. That is what we categorize as a cryosphere. So now you understand what solid Earth means. Now, geophysics, that means we are going to study the physics of the lithosphere. If I'm more precise, okay. So physics of the lithosphere, that is what is generally taught in solid Earth geophysics. Now, geophysics in general is generally studied in two branches. Okay, one is the solid Earth geophysics, and the other one is called exploration geophysics. So in solid earth geophysics, we will mostly learn about the principles of the different physical phenomena which are associated with someone needs to mute, I guess. Yeah, all right. So in the solid earth geophysics, we will mostly learn about the principles that is applicable of principles of physics which are applicable in the solid earth. And in exploration geophysics, what we generally do, we use those principles, use the principle that we learn in solid earth geophysics to explore the earth, explore the mother earth. Now, why do we need to explore the mother earth? Of course, one reason can be, just for the sake of exploring it, to understand how it is. But then there is another greater cause. Okay, as you know, the earth, of course, is the house of several minerals, oil and gas, all the natural resources. There is a word that either you grow it or dig it. Anything we use or we consume, you have to either grow it or you have to dig it. So anything that you want to dig must be explored. You must understand where they are, how big they are, what is their economic importance. Any natural resources, be it iron, be it oil and gas, be it any other minerals, okay, that needs to be explored. So such exploration is often done by the use of geophysical techniques. So we will, of course, we will learn solid earth geophysics, but we will have a lot of references around exploration, how they are used for exploration as well. That is what we are going to look at too. Okay. So this is more or less what we are expecting to understand in this is the context of solid earth geophysics. Now, of course, our syllabus, if we look at, okay, it is generally divided into several chapters. So the first chapter, the first thing we were going to deal with is internal structure of the earth. And plate tectonics, okay? Now, this is, I think, most of you have gone through this to some extent during your, core courses. Okay, I'm sure you have some idea about this thing. So there will be some things which are repetitions. There will be some things which are new. But nevertheless, it's a good time that we brush up our understanding about the internal structure of the earth and the plate tectonics. Ask any questions that you need clarification, and I tell you, this is the very basics of earth science. The very basic, the foundation of earth science is kind of holding on this particular subject. So let us spend some good amount of time to familiarize ourselves and solve any doubt that we might have on this particular topic. Then we are going to study about the gravity and gravitational techniques. Okay. Then we are going to study the magnetics. Now, not any magnetism. We are mostly going to focus on the Earth's magnetism, and then we are going to study about propagation of elastic waves through Earth, and this has a special name which we call seismic. And seismic generally has two branches. One is, of course, we call as earthquake seismology. So we're going to study about earthquakes, earthquake seismology, and then there is something called exploration seismology. So that is nothing but the study of the propagation of the elastic waves through the Earth's crust. Okay. Then we are going to study about resistivity technique, magnetotelluric. Sorry. Uh, then some petrophysics or rock physics, and then we are going to study about, I'm not, geothermal. Okay, this is more or less your syllabus is. Yeah. So gravitational techniques, magnetics, propagation of elastic waves, resistivity, magnetotelluric, and some petrophysics and geothermal energy. Okay, so that is the introduction of the class. I'll stop here for some time and take any question that you might have.
So what does magnetotellurics actually mean?
Magnetotelluric is electromagnetic actually. It's long wave electromagnetic signals.
Okay, sir.
Any other questions? All right. Then let us just start our class. And here I will essentially put the class on record. Okay, it's already recording. Who pressed the recording?
Sir, I started the recording because
thank you very much. Actually, I forgot in the beginning. So okay,
uh,
that is very good.
yeah, like we don't have two people in the class today, and they both messaged me that one had a clashing slot and other one was sick, so they asked me to record.
No, that's
That's what
fine.
they
So
decided.
yeah, so what you need to do, you need to send me the recording so that I can upload it. Okay, because you have pressed the recording. I don't think it will come to my drive. It will come to your drive. Okay.
Okay.
Yeah. Please make sure that you send me the recording.
Yes, sir.
Are the slides visible to you guys?
Yes.
Okay. So let's start with our first topic, internal structure of the Earth. Okay. So you can see here our beautiful Mother Earth seen uh, from the moon. How beautiful it looks. So let me begin this particular class with a nice story. Okay. Before we become very serious about the course, and I'm sure most of you have learned about this particular story during your childhood, and this is the story of Goldilocks. So Goldilocks is this little girl who is actually lost in the jungle, and then she finds a small hut, and when she enters that particular hut, she finds a dining table, and the dining table has three bowls of soups. Okay, so there is a big bowl which she tastes and says too hot. Okay. There is a medium-sized bowl which she takes and says too cold. Okay, and then she finds a smaller bowl. She takes that and says just right. So Earth is called the Goldilocks planet. You know why? Because it is situated at a distance from the sun, so precisely. It's like a blessing that it's not too hot, not too cold. So because it is not too hot and not too cold, what has happened? Earth has an atmosphere which has free oxygen, and Earth has water which is in the liquid form. So what that had resulted is life in the Earth. So in a sense, that is like an accident. If it would have been any different, it would have not been just right, and life would have possibly not been flourishing here. So that's amazing. So with that reference, if we look, and we already know about the internal structure of the Earth. We can generally divide the internal structure of the Earth in two ways. One is called the physical layering, the other one is called chemical layering. Okay, so physical layering means the property of each layer is different physically, and chemical layering means the chemical composition of the different layers are different, right? So if we first talk about the chemical layering, in terms of chemical layering, we generally subdivide the internal structure of the Earth from the surface to the core, to the center of the Earth. We generally call crust, then mantle, and then of course the core. These are the three general subdivision: crust, mantle, and core. This is the chemical layering of the Earth. And of course, the crust has upper crust and lower crust. The mantle has upper mantle and lower mantle, and the core has inner core and outer core. Now you can see in this particular picture the different diameters of these layers have been given. You can see that the radius of the Earth is around in the range of 6371 kilometers. Okay, so the distance from the surface to the inner core outer layer is like 5140 kilometer. The outer core sits at 2383 kilometer. Okay, so the crust could be at the range of all the way up to 100 kilometer thick. Sometimes general thickness of the crust is around 35 kilometers. Okay, but it can be all the way up to 100 kilometer. And then you have the upper mantle and the lower mantle. So this is in general the chemically this is how you can differentiate the Earth. Okay, but if you want to physically if you want to study the physical layering of the Earth, the layering goes like this. So you have the lithosphere, which is the cool, rigid, brittle, and that is generally constituent of the upper crust, which is all the way up to can be all the way up to 100 kilometers. Can be all the way up to say 50 kilometers or so. And then you have, depends on the thickness of the crust, of course. Say half of the crust is generally lithosphere, and the lower crust and the upper mantle, which is hot, weak, and plastic. Okay, so it behaves like a fluid. That is what we call as the asthenosphere, and then the rest of the mantle is called mesosphere. This is very hot, but this is strong. This is solid. So the lower mantle is generally solid, and this is what we call as the mesosphere. Then of course you have your outer core and inner core. So this is how we generally subdivide Earth's different layers, one physically, another chemically. Now let me ask you a question. What do you think about mantle's chemical properties, whether it is solid, it is liquid, it is, what is your idea? Can someone tell me? How do you think mantle is? Anyone? Yeah, please go ahead, share.
Sir, so mantle in short term, mantle exhibits solid properties, but in long term, or like in a, if you consider a great period of time, then you can see that it shows many liquid like properties as well, like they have convection currents and etc. So
Excellent answer. Excellent. That so you know the answer. Okay. So you are absolutely right. So it depends on the time of observation. So say for example, the elastic waves do propagate through mantle. Okay. Say for example, we can see that the earthquakes. If you create an earthquake, the elastic wave will propagate through it. So that means it has, in short time frame, it has solid-like properties. And as you have rightly said, that if we increase the time of observation, then it behaves as a fluid or a liquid, because convection cycle actually works in mantle as well. So the easiest analogy of mantle is like the asphalt or pitch that is generally used to make the roads. I'm sure you all have seen it. So what you can do, you can take a lump of asphalt, okay, and you can try to squeeze it very slowly. Okay, you will see, it will act as a fluid. It will behave as a fluid. Okay, but then you take a lump of the same pitch, or asphalt, and then you like make a ball and throw it very quickly, or in a with force, with some on a glass door, the glass door will break. So will the asphalt. So there is an elastic collision. So that generally doesn't happen for fluid, right? So what we are changing in these two experiments is the strain rate, the way we are trying to deform the body. In one case, we are applying the force very rapidly, and the other case we are applying the force very slowly. So same happens in case of mantle. If the process happens very slowly, it behaves as a fluid. uh, if the process happens very fast, it behaves as a, sorry, I said the other way around. If the process happens very fast, it behaves as a solid, and if the process happens very slowly, then it behaves as a liquid. Okay? So that's good. So now, if we look more closely, so first we are going to talk about the chemical layering, right? So the core, mantle, and the crust. So core is generally very dense. It is mostly made up of iron and nickel. The inner core is generally thought to be solid. The outer core is thought to be liquid. Why? We will, and how people know about this, we will talk about it later on. Just to touch upon right now, what we can see, that the shear wave, the shear elastic wave, do not propagate through outer core. Okay, so if you create an earthquake at the surface of the earth, okay, so there are two types of waves that you generate. One is called P wave, or the compressional wave, and the other one is called the shear wave, or the S wave. What is generally seen, that the P wave do propagate through the outer core, but the S wave doesn't propagate through the outer core. Okay, so that's why you know that the outer core is perhaps liquid. And there is this outer core has also a very important property, that that this is there is a particular current that goes on. There is a particular cycle that goes on in outer core, which we call as eddies current. Okay, and that particular eddies current is responsible for the magnetic field of the earth. Okay, what is being thought, although it is very controversial and people have many hypotheses around it, and many people do not believe on this particular hypothesis, that there is, some sort of the metals that are present there are in their ionic form, and those ions, when they kind of make a circle, they kind of rotate. That creates an electric or a magnetic field, which is essentially responsible for the magnetic field of the Earth. Okay, but we will talk about in more details when we talk about magnetism. And then we have mantle, which is less dense than the core. This generally consists of iron and magnesium silicate. This is mostly solid, and upper mantle is partially molten. Okay, so the upper mantle is partially molten, which is the part of the asthenosphere. Okay, now the composition of the crust is which is the outermost layer, which is very thin and rigid. The continental crust, the crust that makes the continents, which is mostly made up of granite, has a density of around 2.8 gram per cc. And then the oceanic crust, which is mostly made up of basalt, which is slightly heavier, which is a density of 3 gram per cc. Okay. So generally the composition of crust is denoted as Cl, because most of the minerals that you observe in case of the crust are aluminosilicates. Okay, and in case of mantle we call it as Cma, okay? Because most of the minerals that you observe in mantle are magnesium aluminum silicate. It doesn't mean it doesn't have aluminum. It does have aluminum, but together with that it does have magnesium as well. Okay, so magnesium aluminum silicate, and that is what we call Cma, and the crust is called Cl because it is mostly made up of aluminum silicates. Okay. Now, this is a very important slide, because most of you will appear for these national level exams, maybe for the Geological Survey of India or NET or GATE, and this is a slide that I will kind of urge you to kind of completely mug up, simply because what they ask you is the name of the different boundaries which are present between different layers. Okay, and every alternate year people do ask questions around it. Okay, so one of the things that we will do during the course, I will keep on hinting you towards the important things which are generally asked in the national level exams as well. Okay, because solid earth geophysics, there will be many geochemistry and related courses throughout your 5 years, next 3 years journey in the ES department. But unfortunately, this is the only course where you will study physics of the earth, but which is equally important. But due to our constraints here in IISER Bhopal, this is the only course we can offer right now. But that doesn't mean people, while you go for your national level exams, you will not be asked questions on solid earth geophysics, right? So, and this is a very important subject that you should also master, because this is a foundation subject, a fundamental subject. So what I will do, I will sometime go a little bit beyond the syllabus as well, so that I can cover the syllabus for the national level exams as well, and I'll keep on hinting you the areas where people do ask questions there, right? So what this particular slide shows are the different boundaries between the layers. Okay, so the boundary between upper crust and lower crust is called Conrod discontinuity. Okay, the boundary between crust and upper mantle is called Mohorovic discontinuity, or just Moho. The boundary between upper and lower mantle is called Repiti discontinuity. The discontinuity between lower mantle and outer core is called Gutenberg discontinuity, and the discontinuity between outer and inner core is called layman discontinuity. Okay, I think you have to remember these few discontinuities, and also you can actually the better thing will be in the previous slide I have given you the different depths. So you need to know each discontinuity and their more or less at what depth do they occur generally. Okay. So any questions so far? Okay. So now one thing that you might ask, how do we know about the internal structure of the earth? How do we know where is our mantle, how the mantle looks like? How do we know how the core is, and so on and so forth? Because although there is a movie called Journey to the Center of the Earth, for very practical reasons, we cannot go there, right? And there are hardly, so what is the data on which we are actually dependent on to infer about the composition of the and the structure of the earth? What are the data that we are actually dependent on? Okay, and I will tell you all of them are like indirect evidences. So the deepest place where people could go, I mean, not people, what we can do, we can drill wells, right? We can drill wells and then take out samples, like we can drill holes in the ground and take out samples and study them. The deepest we can go all the way up to maybe 5 or 6 kilometers, not more than that. So after 5 or 6 kilometers, we cannot really penetrate and see what is there. So 5 and 6 kilometers, like with respect to the total length of the Earth's radius is nothing, right? So how do we infer uh, about the internal structure of the Earth? What are the different data sets we should look at? So we are going to briefly introduce you to such data sets. So the first thing is, of course, meteorites. Okay, so we know that fundamentally all the planets formed in the same way. Okay, and the meteorites are like the structure, the composition should be very similar to the primitive Earth, right? Very similar to the primitive Earth before it actually became and solidified and formed the Earth by itself, right? So we can, and we do get to see meteorites falling at regular intervals on the surface of the Earth. So we can study their composition and understand how the pristine Earth's composition could have been. Now, seismic waves, we have been talking about it. That is a very fantastic tool by which you can understand how the internal structure of the Earth is. Because elastic waves have different travel time and different properties. They reflect and refract differently while they actually change mediums, right? So we will later on learn there is something called acoustic impedance. So about Snell's law in case of optics, and the refractive index is something that is responsible for for controlling the ray path from one medium to the other. Similarly, there is something called acoustic impedance in case of the Earth, where between two layers, how a particular seismic wave or an elastic wave would propagate depends on, okay, the difference in the acoustic impedance. Now, acoustic impedance is a product of the density and the velocity of the elastic wave, right? So it has a component of density. So somehow, if you can study the seismic wave, you can have also an idea about how the density distribution of the Earth is. Okay, how if I go from the top to the bottom, how such densities are distributed. Okay, so seismic waves are also great tools. So the elastic wave, seismic means the elastic waves. The elastic waves, either it can originate from earthquake, or you can actually create seismic wave with different instruments, which we will study later on. And you can study those waves when, with some receiver signals, and then you can talk about the internal structure of the earth. Of course, there are volcanoes. So what happens in volcanoes, that in those places the crust is extremely thin, okay, and the very hot molten material from the asthenosphere comes out to the surface, right? So if you study those, you will have also a great knowledge about the internal structure of the earth. Then, of course, we were talking about the elastic waves, like the P waves, which are the primary waves. Of course, we will learn about them in a greater detail. But the P waves, the very similar. The analogy is very similar to the pull and push motion of a spring, because the individual particles actually oscillate in the same direction of the wave propagation. Okay, it travels very fast. It can travel through solid and liquid both. Okay, it's the push and pull movement, and that is what we call P wave, primary wave, or a compressional wave. Okay. Similarly, we have something called S wave, or the secondary waves or shear waves. Okay, which moves side by side. So the particle motion is like perpendicular to the direction of the wave propagation. That is generally a little bit slower than the P wave, but the most important thing is it travels through solid only. Okay, so now so you have a source, you are propagating P wave and S wave, and you see in one medium both P wave and S wave propagates, and in the second medium only the P wave propagates, the S wave doesn't propagate. So it will give you an immediate hint that what could that second particular layer be. So the first layer, of course, would be solid. The second layer that we are looking at could be fluid or liquid, right? So that is exactly what is being shown here. So you can see here, like this is the place where such elastic wave is being generated. Okay, and maybe on the other side of the earth, there are many seismic receptors where the waves are being received. So what we can see that so what we are observing in case of P wave, that is like propagating through everything, both so it goes from solid to liquid, but then again comes back to this place. But of course it is being reflected and refracted, which is a different story. We will discuss about the P wave shadow zone, why there is nothing detected here later on. But the moral of the story is you can actually detect P wave from this source on the other side of the earth, simply because the P wave actually propagates through the solid, liquid, and everything, right? But in case of S wave, what we are observing, because it cannot propagate through the liquid, which is the outer core, there is a large zone of S wave shadow. Okay, that means in this side, if we have receptors, we will not be able to receive any S wave, simply because the S wave is kind of dumped at the outer core. So, and that gives you a direct evidence, an indirect evidence that perhaps the outer core is actually fluid, right? Yeah. So that is what we have just talked about. We will talk about it. Talk about it later on. Okay. So now that is so if we kind of combine all sorts of different data sources that we have talked about, be volcanoes, be the earthquakes and the elastic wave propagation, be the your meteorites, if we can't kind of combine all these things together for a period of time, and there is of course then modeling, you can kind of come up with a beautiful layering of the earth and earth, both physically and chemically. Okay. So we have talked about this, I think, in greater length. We don't need to repeat again. Okay, so of course, if we now look at the lithosphere in greater details, of course, the lithosphere has two parts of the continental crust and the oceanic crust, and then of course you have the upper mantle. So this mostly contains the continents contains granite type of rocks like quartz, feldspar. These are the common minerals. The density here is around 2.8 gram per cc. We already talked about it. So the oceanic crust is formed by basalt. We also talked about this, and this is slightly denser too. Okay, so lithosphere is the rigid layer of the crust and mantle overlying the partially molten asthenosphere. Okay. Okay. So next class onwards, we are going to start venturing into plate tectonics and further details of the internal structure of the Earth. But this was mostly an introduction. So this is where I want to stop today, unless if you have any question.
So I have a doubt.
Yes, please.
As we discussed the discontinuities between the crush, mantle, and core, the upper
Mm-hmm.
mantle, lower mantle, like that. So, are there any discontinuities between the physical layers like lithosphere, asthenosphere, mesosphere?
Yeah, they are there. You can look through them as well. There are names, but then they are not very well known, to be honest. I think they have some layer name like D1, D2, D3, something like that. Okay, that is there in Lowry's book. You can find it out. There are names, yeah, but they are not
Okay,
very well known. Okay,
okay, sir.
not well known. Not that is not the right word, I guess. They are not discussed a lot, to be honest. But there are names, of course. Yeah,
Okay, sir. We'll check out.
yeah. Anything else? Okay, another thing I want to tell you before we end this class is, uh, so don't expect in the class that everything is being taught. So I have given you the names of two important books, mostly Lowry. So what is expected if you want to learn the subject? What is expected that you understand. So what will be discussed in the class is the direction through which along which you should study. So if you want to really get a grasp on the subject, what you must do is to go back every day and study what is being written on the books. Okay, there is no replacement of textbooks. Okay, textbooks are absolutely important. So I must emphasize that what you need to do if you want to have a good grasp on this particular subject, you must go back every day and study, maybe for an hour, and that's it, on what has been taught in the class, and go a little bit further. Okay, don't just stop where I have stopped, because I cannot cover the whole book. What you have to do, you have to study some things, because I have to cover the syllabus. So my job is to kind of facilitate you to the right direction, and then we can have a discussion if you don't understand anything, which I am always open to. You can ask your previous classes as well, and I'm very open to discussions. So it's your responsibility to go back and study by yourself, and come back and ask questions which you have not understood. Okay, any other question? Okay, if not, then I will stop it here. And yeah, I will see you tomorrow, same time. Thank you very much, guys.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.